Okay, couple of quick announcements before we start while I wait for the projector to warm up. Those of you who are in EE 100 or in EE 43, some fraction of you have already been to the lab. You've noticed, so the first lab is pretty easy. Well, besides hopefully some of you didn't burn your hands, but other than that, it's pretty straightforward. You may or may not need access to an instructional account on the EECS cluster. If you already have an instructional account, if you're already an EECS student and have an account on the EECS cluster, that's fine. But if not, I have account sheets here that you can get an account for yourself, okay? I'm not going to give them out now. I'll just have them here. At the end of class, you just swing by and I'll give you a sheet, okay? And you will need those accounts periodically through the course, so you should have some. And other than that, one more announcement related to the labs. So the first lab really didn't require you to do any prep going into the lab. It's just teaching you how to use a soldering iron and some basic lab stuff. The second lab onwards, there's a little bit of prep you're going to have to do ahead of time. So if you go to the BSpace website, under resources, ahead of time, usually probably today, tomorrow, certainly by Friday, I will upload the lab for the following week. It is your responsibility to download that lab, look at it, and if there's any pre-lab work you need to do, make sure it gets done in time for your lab. Okay? This is only for EE43 and EE100 students, not for people who are not taking the labs, obviously. Okay? Okay, so let's get started. Today what we are going to do is we are going to finish up the section on the introduction, where basically we're going to start getting into the real material. And then depending on how we're doing on time, I will start talking about resistive circuits. I have another set of handouts for you that I'll give out to you depending on where we are. I'll either give them out today or I'll just give them out in the next class. There will be, just to give you some timetable information, I will be giving you a homework next Wednesday, okay? And it'll be due the following Wednesday. And it's going to be on resistive circuits. Also, some people were asking when the first test is likely to be. It will be in the last week of September, okay? So roughly a month into the course. It'll be, I can tell you, what possible classes it'll be, and I'll work out the precise date a little bit closer. The tests will either be on the 28th or 28th of September or the 30th. Okay? That's test one. Yes? Can I get another of these slides? Sure. Okay? And each test will be roughly a month apart, in some cases a little bit less. It's going to depend on where we are in the course notes. Okay, and probably a week before the test, I will tell you what the precise syllabus for the test will be. Okay, so let's get started. What we are going to do today is we will continue with our discussion, maybe. We will continue with our discussion. Maybe not. Let's try that again. Good. All right. We'll continue with our discussion of the integrated circuit. So, remember, in the 1950s, we already had the ability to make individual transistors. We had resistors. You dealt with them in your labs. You dealt with You haven't dealt with individual transistors yet. We had diodes. We had things like coherers and vacuum tubes, etc. But we had not yet got the ability to put massive amounts of functionality in a really small space. Okay, let me ask you a question. So how many of you have written some software code before? Most of you. Okay. All of you have heard of the term bug, right, in software. Do you know where that term, we don't know that this is true. After the fact, people say that this is true. Do you know the story of where the term bug came from? Yes?
One of the old vacuum tube computers,
Uh-huh.
rooms, had a small, at some point, an actual moth bug, real thing, flew in there and got into the wiring and caused the computer to go haywire.
Right. That's the anecdotal story. We don't know if it's true or not. The anecdotal story is in the ENIAC, which was an early vacuum tube-based computer the size of a room. A moth flew into the room, landed on a pair of wires, got fried, and shorted them out. Okay? And so the computer stopped working. That was where the term bug came from. Now, we don't know if that's true, but that is what people say happened. And that's where the term bug came from. Now, that points out one of the problems people were dealing with before integrated circuits became available. That is, the sheer complexity of the things we were trying to do meant that the wiring got crazy. If you take a modern integrated circuit, the length of wire on some single integrated circuits is sufficient to span the globe on a single chip if you put all the wire end to end. Okay, so there's ridiculous amounts of complexity on modern circuits. And actually, even on circuits from 50 years ago, there was ridiculous amounts of complexity. And with complexity goes cost. So the famous statement from an old chairman of IBM was, I think the entire computer needs of the world can be handled by 3 computers. Okay, this was the chairman of IBM who said that. Okay? And the reason he said that was not because, well, partly he couldn't see into the future, but of course, part of it was the costs were so high that even if you could imagine applications for computers, you would say, why would anybody pay $1 million to do that? That just didn't make sense. So what the integrated circuit enabled was it enabled us to put much more complexity on something much, much cheaper. And so instead of just using computers for financial modeling and weather modeling, by the way, all the early computers that were developed were really developed with the goal of weather modeling. Okay, that's what weather modeling, and then the big advances were simulation of nuclear explosions, where that really drove the development of computers. Okay? But once computers became cheap enough, you could start thinking about using them for other things. You could start thinking about calculators, or you could start thinking about video games, and so on and so forth. And now, of course, computers are completely driven by video games, by far. You know, there's no doubt that modern computers are entirely driven by video games. Okay, now, why? Why have we got this reduction in cost? Because what we are able to do, instead of having a million components wired together by hand, we fabricate them all at the same time on a chip, and we wire them in a very, very automated structural way. Okay? And that's called the integrated circuit. And so you can put 1 billion transistors on an integrated circuit, and the cost of that integrated circuit is not significantly different than the cost of 1 transistor. So what that allows you to do is get a lot of complexity. Now, let's actually, I'll come to this in a few minutes. What is a circuit to you? So I've been using this term circuit. What does a circuit mean to you? And how is a circuit different from an individual device? Yeah. Okay, fair enough. That's a pretty good description. A circuit is a functional unit. Let's add a little bit more onto that. It's a functional unit composed of multiple devices interconnected together. Right? That would be a reasonable description of a circuit. And there's various levels of circuits. Circuits can be a few transistors through millions or billions of transistors. And that's a reasonable description of a circuit. In this class, what we are going to do for the bulk of this course is we are going to learn how to primarily analyze, not so much design, but primarily analyze relatively simple circuits. Circuits with tens of components, maybe at most a couple of hundred components, and we'll learn how to analyze how they work, how to simplify them to get a functional description. So if I were to give you an arbitrary circuit with 10 resistors and 5 transistors, you'd be able to take it and you'd be able to calculate, hey, that circuit generates a little beeping sound, or something along those lines. Okay, so that's why ICs are important, because they give us tremendous functionality at low cost. All right, now, state-of-the-art ICs have gotten tremendously complex. So state-of-the-art ICs are made where individual transistors have dimensions on the order of 10 nanometers. Okay? So that means in a chip that is roughly the width of a human hair, the entire chip is roughly the width of a human hair, we are fitting on the order of 10,000 transistors. Okay? You may be aware of this. How many of you have heard of RFID? Okay. What have you heard about RFID? Yeah. Okay, well, what is RFID to you? Okay, fair enough. That's a very specific kind of RFID, but broadly speaking, RFID is radio frequency identification, right? And what it's used for is to send information over short distances. Depends on the type of RFID. Fast Track is an active RFID system. It has a range of about 10 meters. Okay? The simplest RFID is actually something called EAS. So I'm going to teach you your first way to fight the man. Okay? In this class, we're going to spend a lot of time figuring out how to fight the man. So this is Berkeley after all, right? So if you go to Gap and you want to shoplift, okay, at the end of this course, you will know how to do it. Okay? Because we can beat their simple RFID systems very easily. Okay? But I'm not going to tell you now. Maybe the student who does best in the class, I will tell you how to beat Gap. In fact, I know all the major EAS, which is the anti-theft RFID systems. I know how all of them work. So you can come, whoever comes first, no shopping for the rest of your life. Okay? So we'll come back to that. All right. Okay. Now, RFID is relatively simple circuits. Typical RFID tags have on the order of 40,000 transistors. There are much simpler circuits than that. You are going to work with very, very simple circuits in this class. You are going to, for the lab, where you're going to build that EEG machine I mentioned, that's built with integrated circuits, each of which contains on the order of 30 to 100 transistors. Not very many transistors. Okay? And when you're doing analysis in this class, you're going to work with circuits that are even simpler than that. They may have no transistors. They may just consist of 5 resistors, or so on and so forth. So what defines a circuit is not a number of transistors or the complexity of it. It is exactly what he said earlier, which is it is something that implements, it's a functional description of a collection of components. And so what you define as a circuit depends on the function. Okay? And we integrate them to contain millions of devices, but they could have much less than that. Okay? And so we'll have circuits that are very simple as well. And in this class, we're going to start at very simple circuits and work our way up. Now, besides describing circuits based on the number of components, we also define circuits into 2 broad categories based on how they process information. And in the last class, we had talked about analog versus digital. So one broad basis on which we separate circuits into 2 categories is based on whether they are analog circuits or digital circuits. Okay? So an analog circuit, for example, might be an amplifier. So an analog circuit could take a weak signal and amplify it. And this would be, for example, the amplifier you use when you're driving your loudspeakers. Or it could perform filtration, or so on and so forth. And these are very common. They're used in a lot of applications. It turns out, even today, salaries for analog designers tend to be higher than salaries for digital designers. So if you happen to have to choose, if you look at paychecks, analog is actually a better way to go, even today. Okay? Just because it's a little harder to do design. So that gets us to the next point. One of the problems with analog circuits is while they allow you to do creative things like doing amplification and filtering or altering of waveforms, because they respond to a continuous range of voltages, they are also susceptible to noise. From the perspective of electrical engineering, let's think about what noise means. Can someone give me an example of noise that you have dealt with in your day-to-day lives from an electrical engineering application? Yes? Okay, radio static, very good one, okay? Where you're trying to listen to a radio signal, it's somewhat weak, and you hear things like clicks or buzzes. What's the origin of that? Okay, that's true. One source of radio static is background radiation. Give me an example. From the Big Bang. Well, that's true. That's a little hard to hear with most radios. That's true. Okay, there is a background level of radiation that's related to the Big Bang, and we picked that up with radio telescopes. Picking it up with your radio in your car and getting a strong signal is a little difficult. Okay. Any other applications? Any other sources of radiation that you can hear? Yeah? Sorry, hold on. What's microwaves, that's true. Or your cell phone, right? When I'm speaking over here, if I had my cell phone on over here, you'll sometimes get that little clicking sound. Okay, and then there was one at the back, yeah?
Multicolored speckling you see in really dim digital photos.
Okay, that's true. That is another source of noise, but that's a little different. We'll talk about that. Maybe we'll talk about that later. That's true. Any others? Yeah? Power lines, that's true. That 60 hertz hum that your ear can pick up. Any others? Yeah? Which one? Us, sure. Humans are actually a tremendous source of noise. In a whole lot of ways, right? So no, we do generate a lot of noise because our bodies are essentially big antenna structures that can interact with objects near them. Lightning is another example. So electrostatic discharge. Sunspots. Okay, when the spots show up on the sun, it affects our ability to detect and transmit information here on Earth. There's lots of them. The issue, yes, go ahead. Okay, so that's a good question. What is the difference functionally between noise and an EMP blast? Okay, you know what EMP is? So it's an electromagnetic pulse. The term came about because the idea was you could do an airburst of a very high explosive, a nuclear bomb, disrupt the ionosphere. So you probably haven't seen this movie. This is from the 1980s, back when people actually worried about nuclear war. It was called The Day After. Anybody seen it? Yeah, it's a very, very old movie. Okay, it was a made-for-TV movie, but it was actually pretty good. And anyway, the EMP the term was first used. I think it was first used to describe that effect, where you would do an airburst of a nuclear bomb, and it would essentially knock out all the electronic equipment nearby. Okay, yeah. Well, it depends on the extent of it. Could it knock out half the United States? I don't think there's any EMP devices that have that kind of range right now. Okay. The last example that you have probably seen of a movie that talked about EMP was that Tom Cruise movie with... No, not Mission Impossible. Where he was the baseball nut. War of the Worlds. War of the Worlds. What did you say? Which one? I don't know. Anyway, War of the Worlds, they had an EMP effect. Where all the cars stopped working because of those lightning shots, that's an EMP effect. Anyway, but she asked a very good question. How can you tell the difference? What is it? Would EMP qualify as noise? Well, it depends. So what defines noise? What is noise? Noise is an unintentional signal that shows up on something you're trying to do. And that's an unintentional signal that could be generated from an external source, or it could be an intrinsic behavior of the device. For example, all devices have a thermal noise associated with the fluctuation of electrons because of temperature. That is an internal noise source to your systems. Okay? EMP is arguably the extreme form of external noise as far as the user is concerned, because he didn't intend for that huge signal to get onto his source. Okay? So noise is essentially stuff we don't want on our signals. But the problem with analog circuits is because they are responding to continuously variable signals, they are also responding to small amounts of noise. So as a result, analog circuits tend to be more susceptible to noise. Okay. Analog circuits functionally are often harder to design in the sense that they tend to be more specific. And you'll see what I mean when I talk about digital design later. But you tend to sort of design them for an as-needed application. And One of the reasons that they tend to be handcrafted is when we do digital design, it's very computerized today. If you want to lay out a microprocessor, if you want to design a microprocessor, you don't have to design every transistor. That's not the way it works. We have these abstracted forms of doing design where we essentially lay out everything we need, and the computer does a lot of the design for us. So it's called computer-aided design. Okay? That's not possible in the analog world. Digital, on the other hand, separates the world into discrete levels. And we talked about these in the last class. We can have discrete voltages, for example, 5 volts and 0 volts, which we might call 1 or 0. Okay? And we call those bits. Anybody know where the word bit came from? Why do we call it a bit? Yeah. Yes, binary digit. It's binary digit. Take the B and the IT, and that's bit. Okay. What's that? Okay. So, all right. Digital circuits perform logic operations. As opposed to amplification, etc., digital circuits perform logical operations like AND, OR, exclusive OR. We'll talk about these, what they mean later. Okay? Now, we create systems out of those. We create memories, we create microprocessors, etc. The big advantage of these systems is because we are separating our information states by large voltages, noise has much less of an effect. If I have a little bit of a wiggle of noise on a digital system, but it's far separated from my ones and zeros, it doesn't matter. The system essentially rejects it. So my 0 isn't exactly 0, it's wiggling between plus 0.01 and minus 0.01. So what? It's not 5. So the digital system treats it as a 0. And so that's the big advantage of digital systems. They're very robust against noise, which means it's much easier to construct really big systems and still have them work. In this class, we're not going to spend a whole lot of time on digital systems. Okay? For those of you who want to learn about digital systems, from a circuit perspective, the first course would be EE 141. From sort of an architectural perspective, EECS 150, and then a whole series of other courses in that range. All right. Digital systems were typically the basis for computers. Having said that, not all computers were digital. There were analog computers before, but all modern computers are digital. Okay? Actually, let's ask a side question. Would you consider a cell phone to be digital or analog? It's both, in fact. And it's what we call mixed signal, where it's partly digital and partly analog. Okay? So the world has gotten more complicated. We tend, especially because consumer electronics has become really big, we don't separate digital and analog as cleanly anymore, and we tend to build a lot of systems that have both. Okay. But going back to digital, if we look at early digital computers, the first truly general-purpose computer was called the ENIAC, and it was used by the Army to calculate how to set the angle and power for artillery shells. Okay, they were used to calculate, essentially, tables for how to fire artillery. And then afterwards, during the Manhattan Project, when they were doing development of nuclear weapons, it was also used for calculations related to the implosion required to set off bombs. Now, as I said earlier, the early computers were huge. They filled up whole rooms. They were made with vacuum tubes. And they were wired by hand. We've talked about the first bug, which, we don't know if that's true or not. That's just anecdotal evidence. And interestingly, most of you have probably heard of a programming language called Ada. The first modern programmer was Ada Lovelace, and that was in the 1840s, okay, way back. Okay, so computers, you know what they are. They've become pretty dominant. We are not going to talk about computers in this class, though obviously you'll use them quite a bit in what you do. Okay, let's start laying out some background information. So we're done with the intro to the course. We are now going to lay out some background information for the rest of the course, and then we will actually start diving into resistive circuits. So, some background information. How many of you are basic science majors? College of Arts and Sciences, or the like. Okay, small number. I assume the rest of you are all College of Engineering? Yeah? Okay. So engineers, unfortunately, have not followed the science rules that have been laid out for units as well as we should have. In science, you are generally supposed to use the SI system of units, the System International, which is essentially a system of units that says we should do everything in what was called the MKS system, okay? Which means meter, kilogram, second system. When we talk about length, we should ideally be doing things in terms of meters. Mass should be measured in kilograms. Time should be measured in seconds, okay? Some derived units that come out of that are measures of current is the ampere, temperature is, of course, the Kelvin, and amount of substance is in moles. In the semiconductor world, we have not fully sold into that. So in the semiconductor world, we routinely use a system called CGS, which is the centimeter gram second system. It still is based on the metric system, but it just means we tend to talk in terms of centimeters. It makes it difficult when you read the same paper written in a physics journal versus written in an electrical engineering journal. You'll see units will often be different. It's just the way it worked out. It's nothing major. It just means you have to do unit conversions when you talk to each other. Okay. But everything we do is going to be metric in this course, I think. I'm trying to think if we're doing any temperature measurements that'll be in Fahrenheit. I don't think so. Everything should be metric. Okay. Now, there are some other units to keep in mind. We have units that are multiples of 10 and that are fractions of 10. You are familiar with these. Kilo, for example, is 1,000. Mega is 1,000,000, so on and so forth. And then milli is 1/1,000th. Micro is 1/1,000,000th, and so on and so forth. Okay. When you consider a typical light bulb, like a fluorescent bulb, for example. Okay, well, one of the compact fluorescents you probably have in your apartment. Anybody know? When you buy a light bulb and you pick the light bulb for your house, what parameter do you use to figure out how bright it's going to be? The watts. What is watts? Power. Okay. Watts is power. All right. Anybody? Okay, well, we'll come back to what power means in a few minutes. Typical compact fluorescent bulb that you put in your room, how many watts is it? Yeah, I just want to know how many watts. Give me a number. If you put a 100-watt compact fluorescent, that's really bright, okay? Yeah, it's usually in the range of 20 to 40 watts. That's pretty cool. Okay, 60 is really, really bright, okay? Okay, so at 20 watts is pretty typical. An equivalent incandescent would be 100 watts. Okay, so let's say 20 watts, something like that. Okay, so you got a 20-watt bulb in your house. That bulb is 20 watts means it's a measure of power. It's how much power it consumes, how much energy it consumes per second. All right. Now, let's look at some other nomenclature issues, and then we'll start talking about what voltage means and what current means and what power means. All right. Many of these units that we talk about, the way we describe them depends on the system that we are describing. For example, some of the systems that we deal with, if I ask you, well, okay, I'm going to give you an example. That bulb she was talking about was a 20-watt bulb, and it's running roughly at 100 volts. Okay? Let's just say it's 100 volts to make our math easy. Okay? Anybody know without, I haven't taught you about power yet, so you may not know the answer. How much current is that drawing on average? 0.2. Yeah, about 0.2 amps, that's right. How many milliamps is that? 200 milliamps, okay? So that's, if you don't know what we're talking about yet, we'll get to it, you'll get there, okay? So it's 0.2 amps. Is that always 0.2 amps? When I turn the bulb on and it's stabilized, if I measure it now, and I measure it 20 seconds from now, and I measure it 22.25 seconds from now, will I always measure 0.2 amps being pulled? No. Why not? The voltage fluctuates? What do you mean by that? That's right. But what do you mean by that? Ah, good. We use AC current, okay, which means we actually use a sinusoid to drive our systems. And the voltage is going up and coming down and going up and coming down. That means the current, when I said the current is on average about 0.2 amps, that didn't mean the instantaneous current. The instantaneous current is actually varying by quite a bit. So we need different ways to describe current or voltage or power in terms of whether it varies with time, whether it's steady state or not. So we have different conventions that exist to do that. For example, if we use a lowercase letter, by the way, I is usually used by engineers to describe current. So if I use a lowercase I, it'll typically indicate a current, but it'll indicate a current that is measured at some instant in time. And maybe it varies with time or maybe it doesn't, but it's an instantaneous measurement of time. If I want to indicate that more explicitly, I will often indicate it by an I followed by a parenthesis within which I will put a T, which means it's a current, it's an instantaneous current that is a function of time. Okay, so that's what this means. And that current could be sinusoidal. It could be perfectly flat. That's fine. But it is a current that I'm defining in an instantaneous way. For current that is not varying with time, current that we are saying is fixed with respect to our analysis with respect to time, we indicate that with a capital I. Okay? And that means it's typically a constant value, which we often call as a DC quantity. DC quantity means direct current, means not alternating current, so not sinusoidal. Okay. Often in these systems and in the textbook, if you see a bold I, that has a specific meaning. So usually that'll be a specific variable. For example, it could be a vector, it could be a variable, something like that, but it has a specific meaning. And that's how the text will use it. In the class, if we give a specific meaning, we'll usually call it out as such. Okay. So having given those definitions of some nomenclature, let's start defining terms. Okay. First, what is the basic unit of current flow? Okay, I didn't ask that question well, but you gave me the right answer anyway. Okay, yeah, that's true. Electrons. Okay, I should have said what is the particle responsible for current flow? What did you say? Yeah, you gave the right answer to the first question I asked, which was not well phrased. Amperes. Okay, so the unit of current is amperes. What I meant to ask was the question you answered correctly when I asked it wrong, which is what is the particle responsible for current flow, which is electrons. Okay, so let's back up because some of you look absolutely confused now. All right, the unit of current flow, namely the unit, for example, such as we would define in these systems of current flow, is the ampere. Okay? What is an ampere? It's a specific measure of how much current flows. Now, what is current flow? If you were to define current flow, and hopefully you remember this from high school physics, it is the flow of charge. What is the minimum unit of charge that exists in nature as we discuss it? It's an electron. Okay, it's a single electron. Okay? We define current based on the amount of charge moving through a plane in a unit of time. Okay? So let me draw on the board an example, if I can find a eraser. Here we go. Let's draw on the board two examples. So I have one plane like that, and I have another plane like that, and actually I'll give you a third example, and I'll have another plane that's exactly the same size. So pretend these two are the same size, and this is roughly a third the size. Okay, I'm going to have a way to look at this plane right here. I've got something that's looking at that plane, and that's watching how many electrons get through. And at time 0, I'll turn on my little telescope that's watching it, and I'll count for exactly 1 second. Okay? And in 1 second, I get 1 electron through, 2 electrons through. Okay? So that means this is 2 electrons per second. Now, I will take this one, it's double the size, and I will do the same thing. And I will count electrons, and let's say, in this case, I have 1, 2, 3, 4 electrons through. So this is 4 electrons per second. And this is also, same 1, 2, 3, 4, 4 electrons per second. Okay, I haven't defined how much charge there is on an electron yet, so let's ignore that for now. Would it be fair to say that the current through this is 2 electrons per second, and the current through that is 4 electrons per second? So it would be fair to say that this has twice the current of this. Okay? Yes, question?
So it's kind of, isn't that only true when you're observing it? When you're observing the plane?
As opposed to?
Not observing it? Don't electrons behave differently when you don't observe them?
Okay, fair enough. Okay, so you are now asking me about wave-particle duality. Okay? So, with respect to measuring current, because it's a macroscopic, I'm going to answer this question. For those of you who don't get it, don't worry. I'm not going to ask you this on a test. With respect to measuring current, because it's a macroscopic phenomenon, it's the average of the integrated wave functions. Okay? So the fact that it doesn't show up as a discretized particle doesn't matter. Okay? So there's still electrons flowing. It's just an aggregate of a wave function, and it doesn't matter. Okay? All right. Those of you who didn't get it, don't worry. You want to learn about that? Take EE 130. All right. Now, so we have 2 electrons per second here. We have 4 electrons per second here. Now you notice something. This box, I didn't draw it so well, but pretend this box is roughly half the size of this box. Okay? So this box is half the size of this box. It so happened that this one had twice the current of this one, but the dimension didn't affect my calculation. I just said, how many electrons go through the plane? I didn't worry about the size of the plane. So current is measured independent of the size of the plane. If I want to know how much current, if I had a wire that was as big as this entire huge board, okay, I don't need to know the size of the board. I'm just sitting there and saying, I'll count how many electrons go through the board. It doesn't matter the board is this big or is huge. So current doesn't matter for the size of the plane. We will introduce later another term that does depend on the size of the plane, and that's called current density. Okay? And current density is defined as the current per square centimeter. So I divide it by the area. Okay? And so that is current density. By the way, we often indicate current density by a J. Okay? All right. Now, my definition so far is not complete. My definition is number of electrons per second. But that's not the definition of current. I told you the definition of current is the net charge crossing the surface area in a time delta t divided by delta t. So it's the net charge per second. Okay? That's our definition of current. What do I need to know that I don't have yet that'll get me from here to there? I need one more piece of information. What is it? Yes?
How much charge is in an electron?
Exactly. How much charge is in an electron? Does anybody know how much charge is in an electron? But before you answer that, what are the units of charge? Coulombs. Okay. How much charge is there in an electron? Okay, 1.6 times 10 to the minus 19, plus or minus. An electron is negatively charged, so there's a minus sign there. Okay? Minus 1.6 times 10 to the minus 19 coulombs. Okay. Is it the charge of an electron fixed? Yeah, it is. Okay. Okay, for the purposes of our analysis, it is. Okay. Don't worry about that. In fact, we always treat charge as fixed, but we allow mass to vary, okay? Anyway, so the charge is fixed. So to get from 2 electrons per second to a measurement of current, all I do is I multiply 2 by 1.6 times 10 to the minus 19, and I now have my answer in coulombs per second, and coulombs per second is defined as an ampere. Okay? So if your answer is 5 coulombs per second, that is by definition 5 amperes. Okay? That's how we do this. Okay, now let's think about this a little bit. This example that I gave you here, I did the measurement for 1 second. Let's take 2 cases. We're going to do it for these 2. Okay? So in this one, let's erase that. In this one, I will measure it for 2 seconds, and I would have measured arbitrarily 6 electrons. Okay, what is the current? Well, it's 3 electrons per second. Okay, so it's 3 electrons per second. But in this one, I measure it for 3 seconds. How many electrons would I get? You made us, you see, answer the question without me having you complete information. You assumed that the current didn't change with time. He said 3 times 3. Okay?
3 times that divided by 3.
3 times what?
3 times 1.6 something.
No, but that's assuming the current doesn't change with time. Don't worry, we'll get to it. Okay? All right, so let's get to it right now. Here, I said, I measured it for 3 seconds, and I measured it for 2 seconds, and I got 6 electrons. If the current doesn't change with time, in other words, it's time invariant, okay? It's a capital I. If I measured it for 3 seconds, how many electrons would I get? I would get 9, okay? But that is only true assuming it doesn't change with time, okay? All right, now let me give you an example where it does change with time, and let's get some definitions. So we'll do it on this one here. Let's say, let me erase all this so we have a little bit more space. So let's say in 1 second, I'm watching this continuously, okay? Every second I've got a little shutter that takes a picture and counts how many electrons I've gotten through. So let's say in 1 second I got 2 electrons, okay? And in 2 seconds I got 4 electrons. And in 3 seconds, I have, so by the way, this is 4 electrons total, okay? And in 3 seconds, I have 9 electrons, okay? So let me ask a question. If I want to know I right at 1 second, actually, let's do it a little bit differently. If I want to know I, where I is my average current, measured over the entire 3 seconds, what is it? It's 3 electrons per second, right? 3 electrons per second. But if I want to know I at 1 second, what is it? It's about 2 electrons per second. So you now see the difference between capital I and small I. Capital I represents essentially the non-varying part, which for a system that has variations tends to be the average. Small I represents the instantaneous part. Yes, question? Sorry, I missed what you said. Start again. Wouldn't what? Oh, you're going to have to speak up. I'm sorry. I have a cold, so I sort of not able to hear that well right now. So you can all call me all sorts of names. I won't hear it. So, go ahead.
Given that you're working on scales of individual electrons, wouldn't the treatment of current as a continuous function of time break down?
Yes. Okay, fair enough. if we are talking about individual electrons, talking about things as a continuum function of time is somewhat problematic because the charge on an electron is quantized. In other words, the charge on an electron is exactly almost exactly 1.6 times 10 to the minus 19. And if we wait half a second or a quarter second, it doesn't mean that we get 0.8 times 10 to the minus 19. We either get 1.6 or 0. Okay? You're right. That's a quantization issue, but we're ignoring it in this class. Okay? And in fact, for anything except some very specific applications, you can almost always ignore it. Okay? There's a couple of subtle computer applications, some cryptography-related applications where they exploit quantization, but otherwise we ignore it. Okay? All right. So we've now seen the difference between capital I and small I. Small I, in particular, when we define it with respect to a particular variable such as time, tells us how current changes at an instantaneous current is changing and what its value is at a particular time. Capital I represents the net charge crossing a surface in some interval divided by that interval, and that will typically be assumed to be non-varying if it's a capital I. Okay? All right. Now, the relationship between charge and current, of course, is based on the charge on an electron. An electron, as we've already answered, has a charge of, it's negative, so it's minus 1.6 times 10 to the minus 19 coulombs. Okay? Now, there are some rules that we're going to use for some of our work. Let me give you some statements about charge, and then we'll talk about the implications of them. First statement, charge can be either positive or negative. Okay, an electron is negative. Can you give me a charge that moves? Well, actually, first, can you give me a charge that moves that is positive? No. That is with respect to the vector associated with current. I'm talking about charge. Well, no, hold on. I didn't ask you about current. I asked you about charge. Charge is not a vector. It does not depend on direction. Okay, so give me a charge that moves. That is positive. Yes. Okay, true. Not something we can observe that easily. Okay? Okay, give me something that you could actually observe that is positive. Yes, the back. Yep. Okay, I agree with that. I'm going to defer that for a second. We'll come back to that. Photon is neutral, yeah. Good, an ion. A hydrogen ion is a good example. Okay, we can get some examples that are closer to what you deal with. To be honest, I don't know what gas they fill these with. Anybody know? Yeah? Are these mercury vapor? I think mercury vapor is yellow. I don't think white is mercury vapor. So anyway, it doesn't matter. Good example, mercury vapor. Okay, mercury vapor has a mercury coating inside, it ionizes, and you actually get some mercury ions moving. Okay, there are other examples: xenon, argon, that we ionize. I think this has actually a fair amount of argon in here. Mercury vapor is used in the yellow street lamps. The bright yellow is sodium. The yellowish, soft yellow is a mercury vapor. I'm not sure this is mercury. Okay? I don't know what it is. A homework assignment for me and you. Okay? We'll go figure out what these are. So I'm pretty sure this is not a mercury ionization spike because that's a little bit. That has a more fixed emission spectrum. This is white. Okay? All right. Anyway, we'll figure it out. So good example, ions. Okay? Ions are examples of things that we can observe that can be positively charged. Okay? Now, he said holes. Does anybody know what a hole is? Come on, answer the question. Yes. Yes, in fact, that's correct. A hole is not a real particle. It's simply an absence of an electron. And from a mathematical perspective, it turns out it's very easy. It makes our life really easy if we model the absence of an electron as a new particle, which doesn't exist, that we call a hole. Okay? In this class, you will not really deal with holes. But if you take EE 130, you will actually deal with holes. Okay? A hole is just an absence of an electron, but it turns out we can model it as a particle that's opposite in charge, but not exactly the same in mass. And that turns out to be why it's very convenient to model it as a hole. Okay? But we're not going to talk about it in this course. Okay, so charge can be either positive or negative. As we've already discussed, the fundamental quantity of charge is that of a single electron or a proton, okay, which would be positive. Of course, we don't really deal with proton transmission in our typical semiconductor devices. And its magnitude is denoted by the letter E if you're a physicist. Engineers often also use another letter. Anybody know what letter that is? Q. Okay, Q is commonly used. In many textbooks, you will see Q used to denote the charge on an electron. Okay, E or Q. Okay, now we get to a very important law that's going to be very useful for us throughout this course. And that is, according to the law of conservation of charge, in a closed region, so it's a self-contained region, charge can be neither created nor destroyed. What that means is, if I have a box and it has a certain amount of charge in it, arbitrarily 3 coulombs, it'll always have 3 coulombs. If it goes to 4 coulombs, the only way I can make it go to 4 is by somehow pushing some charge into it. To get it down to 2 coulombs, the only way is by pulling charge out of it. Okay? What's that? Good point. So he made a statement which is an underlying basis for this. He said, well, it's related somehow to energy because we don't create or destroy energy per se. It actually has to do with work. There's a relationship between charge and work. Okay, and we'll talk about what that means in a few minutes. Okay. Now, getting to that point for charge and work, another statement that I'm going to make is like charges repel and opposite charges attract. Okay? And, of course, we already have now a definition for current. That is I, instantaneous current, is dq dt. Instantaneous current is equal to number of coulombs per second or rate of change of charge. Okay? And this is our definition of current. Okay. What does that mean with respect to a wire? Okay, if I said, I'm going to give you a circuit, and the circuit I'm going to give you is this circuit over here. It is a battery. Okay, this is how we denote a battery. We have 2 lines, one larger than the other. Positive is the larger line and negative is the smaller line. And I connect it across this. What is this? It's a resistor, okay? And I connect the resistor across the battery. Okay, I'll give you a battery, a 9-volt battery, and I'll connect a resistor across it. And I'm going to wait a certain amount of time, and then I'm going to ask you, what changes do you expect to happen physically to the system? What would you, let's say I wait 10 seconds. What changes could you observe? Yeah. The resistor will heat up. Why? Hold on one sec. Let's finish the answer. Okay, you're converting you're essentially generating thermal energy by converting electrical energy. Okay, that's true. That's correct. Okay, that's a reasonable way of describing it. We'll get into more details on that later. So we are essentially generating heat. Okay, that's true. So the first point is you are going to heat up the resistor. Okay, anything else will happen 5 or 10 seconds into it, or even a minute or an hour into it. What else? What else will happen? Yep. The battery will? Yes, the battery will deplete. And how will I know it depletes? Okay, the current stops flowing, and over time the voltage in the battery will drop. And ultimately that resistor will stop heating up because the battery runs out of juice. Right? So that's correct. Yep.
If it's not an ideal set of wires, the wires are going to heat up a little.
Yes, that's true. If they're not an ideal set of wires, the wires would heat up a little. In practice, Unless this was a really low resistor value, the resistor should be really what heats up. Yep. As the voltage goes down, the current will also drop. Good. Okay, we haven't talked about why, but there's a reason for that related to something called Ohm's law, which you've all heard about or learned about before. Okay, correct. Okay, so there's all these things that happen. But what is physically happening in the wire? Electrons are actually moving through the wire. Now, it's not the same electron going all the way through. Okay? What actually happens is there's a local electron motion, and electrons knock other electrons, which knock other electrons, which knock other electrons, and that's how we measure current flow. So it's not like we've got this one electron that we've marked, and we can watch it go all the way through the circuit. In fact, what happens is this electron passes its energy on to the next electron by knocking into it, and so on and so forth. But on average, there is motion of electrons such that we have electrons flowing this way. Electrons flow from the negative to the positive. Yet, as you learned in high school physics, we denote current flow as going from positive to negative. Okay? Some English textbooks, not in the US, and in fact not in most countries, but some English textbooks you will sometimes see showing current going in the same direction as electrons. And the reason for that is they correctly wanted to fix this. They wanted to say, well, it's silly to talk about current going opposite to electrons. Let's fix it. So they had a movement in English academia to try to change it, and this was in the 70s and 80s. And obviously it went nowhere. But you might find some texts that do that. Just be aware of that. Okay? But any text we use in this class or that you're likely to see for most of your life will show current going in the opposite direction to the direction of electrons. Okay, so we've defined current. Now, that was a system where we only talked about electrons. Let's take another system. Let's take a system where I have electrons and ions, or protons, okay? And the electron has a negative charge, and the ion has a positive charge, okay? And let's just say they are moving in opposite directions, like so. The total current is the sum of the two. Because they are going in opposite directions, but they are opposite in charge, we add the numbers together. So we can calculate, let's say I have 2 electrons per second and 2 ions per second. What is the actual current? What's that? Well, that's the velocity, but I'm giving you now a number. I'm saying assume it's 2 electrons per second going right to left, and 2 ions per second going left to right. Okay? What is the actual current? It's 4 roughly electrons per second, right? It's 4 charges per second. That's the number. Okay? Why is that? Because they are going in opposite directions, but the charges are opposite as well. Now, this gets me to a point, something that I said to you earlier. You said earlier, well, it depends on the direction. That's for current, not for charge. Charge is not a vector. Charge is a scalar. It doesn't depend on orientation. Current is a vector. The direction matters. Okay? Now, if we have the same situation, but the positive and negative charges are both going in the same direction, the math changes because now we have a positive and negative going in the same direction. So let's take that same example. 2 electrons going left to right, and 2 ions going, positively charged ions, going left to right. What's the current? 0. That's true. So the mere fact that you have motion of electrons does not mean you have current. You have to have a net motion of charge. Okay? So in this case, you would have 0 current, despite the fact that you have electrons and holes flowing. Okay. Now, we get to a point of how we actually calculate current. I've sort of worked through it on the board for you here. What we do is we define an area for our device, And our device could be a resistor, it could be a wire, it could be what have you. And in that area, if we want to find the current, we just count at any instant of time how many electrons get through that. Okay, let's go back to the board and let's define a specific example. Okay, this is my plane of my board. I'm going to make my life a little easier. I'm going to do it in 1D. Okay, so this is my plane of my board. And let's say my electrons move at 10 centimeters per second. That's the speed of my electrons, okay? My electrons have a velocity, so they move at 10 centimeters per second. That's the velocity of my electrons. And I'm going to just put some axes over here. So let's say this is about 10 cm. This is about 20 cm. This is 0. This is about 30 cm. Okay. I'm going to start at time 0, and I'm going to count for exactly 1 second. That's how I'm going to do my counts. Okay? And let's say I have 1 electron here, I have 1 electron here, I have 1 electron here, and 1 electron here. Okay? And remember, I'm counting from 0 to 1. That's it. 1 second exactly. Okay. In that 1 second, I want you to tell me which electrons are going to get counted. Will this electron be counted? Yes. This one? Yes. This one? No. This electron will have moved somewhere up to here in that time, but it will not have gone through that plane. Okay? So we see, therefore, that two things matter when we are trying to figure out what our current is. We care about the velocity of the electrons, and we care about how many electrons there are spatially distributed. Okay? So, if I have electrons moving at 10 centimeters per second, I'm only counting electrons in this box. And so I would say my current is 2 electrons per second when measured I at 1 second. Okay? Now, let's do the same thing, but let's change the velocity. Let's change the velocity to 20 centimeters per second. Now, what is this number? It's 3 because I get 1 more electron through. Okay? So, what the math says then is you need to count the velocity and you need to take account of the density of electrons. Now, it turns out if you do the math, therefore, and we say things are uniformly distributed. So we say the electrons are uniformly distributed throughout this box, and we will say the density at which they are distributed is n. So it's the number of electrons per unit volume. Then we can define current as Q, I'll explain why in a second, times V times delta T times N times A divided by delta T. Let's take these step by step. Okay, first, why is Q here? What is Q? It's the charge per electron. If I'm taking Q out, that means what I'm left with over here is the number of electrons going through a plane per second. And I multiply by Q to get charge per second. Okay? So this is the number of electrons per second. Okay? The delta T and the delta T accounts for the fact that I'm integrating. So I'm waiting from 0 to 1 second, and then I divide by 1. If I waited from 0 to 2 seconds, I would divide by 2, and so on and so forth. Okay? So that's where the delta T's come from. The V is the velocity. The N is the density. The V tells you how far into the system you go back to count electrons, and the N tells you how many electrons are in that box. So, V times delta T is distance. How far back? If you're doing it for 1 second, so it's 10 centimeters square 10 centimeters per second times 1. If you did it for 2 seconds, it would be 10 centimeters times 2. Gives you the distance back. N gives you the number of electrons per dimension. So 1, 2, 3. And A gives you the area of the plane. Because N is defined as electrons per unit volume. Current is measured with respect to a plane. So we multiply by the area of the plane to get into the right units. And so we then have I is equal to Q times V times delta T times N times A over delta T. And so what this says is I now have a way of, given a box with a certain density of electrons and a certain velocity of electrons, I can figure out the current. Now, I made certain statements there that actually had assumptions lying under them. Can anybody, sometimes I ask questions like this in tests. I probably won't ask it in this class because these are sort of hard questions sometimes. Let's think about some of the assumptions. Can anybody tell me any assumptions I made in this statement? Yes? That's true. I essentially had a single velocity parameter. I assumed all the electrons moved at the same velocity. Absolutely true. Yes? I assumed the charge density is uniform because I kept n as a single number. Those are the two big ones. I assumed uniform velocity and I assumed uniform charge density. Good. Yes? I'm sorry? It's the average velocity, which in a three-dimensional system is calculated from the root mean square. That's right. Okay? Okay. So that is how we often define current. Okay. Now, what does that mean really, though? Let's go into an actual box. Let's go into an actual box that actually has electrons inside it, and let's see what those electrons are doing. Those electrons are not all moving straight across the page. If I apply, excuse me, if I were to put positive 1 volt here and ground here, I would expect the electrons to want to go this way. By the way, I made a statement ground. You all understand that that generally is treated as 0. Okay? So I put positive 1 volt here, ground here. You'd expect the electrons to move this way. But it turns out they don't. We find the electrons are moving in sort of random ways. Why? Brownian motion. Okay, can you explain? Okay, fair enough. That's a reasonable statement. It turns out it's not dominant in electrons, which is Brownian motion. There's sort of random heat-related motion. That is true. It does affect electrons at that level. It's called phonons, but it's not so important for electrons. Yeah?
Each electron repels the other electrons.
That's right. That turns out to be much more important. The electrons are interacting with each other. When the two electrons are traveling this way, if they get close to each other, they push each other apart. For charged particles, charge-related interactions are much, much more important. There is an effect from heat for electrons as well. It's just not that important. Okay? Not at this level. Charge-charge interactions are much more important. So these electrons, not only are they interacting with the applied voltage, they are interacting with each other and pushing each other apart. They also interact with the nuclei of the atoms around them. So they're sitting in this metal, which has atoms inside it, and these atoms have positively charged nuclei, which also cause the electrons to get pushed around. So if we were to look instantaneously, if we had a way to go in and look at what the electrons were doing, they're not all going from right to left or left to right. In fact, they're going in sort of random motions. Then, what does this mean? How can I talk about counting electrons? So what am I saying when I'm saying I'm counting electrons? I'm saying, on average, despite the fact that the velocities are going all over the place, if I were to average out all the velocities of all the electrons, there will be a net velocity vector in a given direction. Okay? And if I put positive 1 volt here and negative 1 volt here, the net velocity vector would be in that direction. Okay? Not all the electrons are instantaneously going in that direction, But average all of them out, and they will have a net velocity in that direction. Okay? Now, the velocity of those electrons, is it high? So that net velocity, this velocity number I talked about, is it higher, lower, or the same as the instantaneous velocity of the electrons? If I were to pick one electron here and look at its velocity, which one would be higher, the velocity of the one electron or the average of them all? The one electron will have a much higher velocity. The average velocity, which what we call the drift velocity, the net velocity, because of this externally applied voltage, is much, much lower than the instantaneous velocity. Okay? Because the instantaneous velocity gets really, really high. Depending on the system, it can get close to the speed of light. Okay? Okay, so that's, yes, question?
So in this case, there's some electrons that would be moving towards the negative
Yeah.
sometimes. So
Yep.
Since we're talking about like velocity, which is a vector,
Uh-huh.
wouldn't that mean that it has a negative direction?
For that individual electron?
Yeah.
Yes.
So that would mean that one of those electrons could actually have a much lower velocity.
Well, it has a negative velocity. The magnitude is still large. It's just going in the opposite direction.
So technically it's speed, right?
Correct. So, okay? So that's what happens in practice. Now, we have enough time to finish up a couple of more concepts, and then we'll be ready to start on resistive circuits. We need to talk about time dependence. We've already started talking about this through what we've been discussing so far. In this course, you are going to see several types of time-dependent circuits, and we will be doing analysis of time-dependent circuits. The first section of this course, the section we're about to start on resistive circuits, we do not look at time dependence per se. Okay? And so, if I say that this circuit has a current of 5 amps going through it, that means it's 5 amps today, it's 5 amps 10 days from now. It's time independent. That is called a DC circuit. DC means direct current, and specifically with respect to time dependence, it means it is time invariant. You have already correctly identified for me AC, alternating current. Alternating current is a sinusoidal system, where there's a sine wave where the current will vary in a sinusoidal fashion with time. In a few weeks, we are going to introduce some specific types of circuits, including resistors and capacitors. And those circuits will show various other types of behavior, including decaying behavior, where the current drops with time, rising behavior, where the current rises with time. We're not really going to talk about this for a while, and this is an example of something that seems to be a combination of two. This is a sinusoidal curve, but it's decaying with time. So we call that a damped oscillation. Okay? And we will see some examples of these late in the course, but they're not really important for what we're going to do. Okay, let's take one example, and then we'll probably have to stop pretty soon. And that is, let's talk about a system where the current is decaying. And let's use that same analysis we used here, figuring out current with respect to time, figuring out the relationship between charge and current, but let's do it for a system that has a decaying behavior. So I'm going to define the system for you. This is my definition. I as a function of t, instantaneous current as a function of time, is equal to, and I'll have two regions of operation. The first region is when t is less than 0, before time 0, the current is 0. When t is greater than 0, it's a falling exponential. So it's 6 times e to the minus 0.2 t. Okay, before we get going, let's look at some specific points. At time 0, or let's call it at time 0 plus, just barely past 0, okay? what is the current? It's 6 amps. I take 6 e to the minus 0.2 t. I'll put in t is equal to 0. And exponent of 0 is, of course, 1, so we get 6. The reason I didn't say at time is equal to 0 is there's a discontinuity at time is equal to 0. So to the left it's 0, to the right it's 6. Okay, at t is equal to infinity. At t is equal to infinity, what is the current? It tending towards 0. At t is equal to infinity, it asymptotes to 0. Okay? So, the shape of the curve then looks like this. Now, we're going to do two things. First, let's determine q as a function of time. This is I as a function of time. Let's determine q as a function of time. So remember our definition we had. I is equal to dq dt. Okay? So if I wanted to find q, what would I do? Differential equations. You're going to integrate, so you're going to move that there. You're going to calculate q is equal to I dt integrated from 0 to t to find q of t. Right? That's what we're going to do. So, actually it shouldn't be 0. This is a mistake. Because I've defined the equation starting from less than 0, I would integrate from minus infinity to t. Okay, because my definition here goes below 0. Okay, so I would integrate from minus infinity to t, I would integrate I. Okay? How do I do that? Well, I have an equation for I. I will plug it in here, and I will integrate from minus infinity to t. So, I take the equation. Life gets easier because, sorry, I should have left that on the board for a second. Life gets easier because I said I is equal to 0 for all t less than 0. That fact allows me to make my life a little easier. How? Because this minus infinity integral now becomes an integral from 0 to t. Because less than t, I apologize, less than 0, I is always 0. Which means all values less than 0 I can ignore. So, therefore, I am basically calculating an integral from 0 to t of this equation right there, 6e to the minus 0.2 times t. And I plug it in, I get the integral, and my answer is q of t is equal to 30 times 1 minus e to the minus 0.2 t. So you now have an equation for q of t. Okay? So that's all there is to it. It's probably time to stop. We don't have time to pick up the second part. We'll pick up the second part in the next class. For those of you who do not have instructional accounts, please just come up to the front and I will give you a sheet to give you an account.